So one thing I wanted to share for tomorrow's quiz, we blasted through integration by parts, and now we're on to partial fractions. Is the question you're going to then wonder is, how do I know what technique to use now, right, when I'm faced with an integral? And one thing I want to share about integration by parts is, I'll make a little note up here, integration by parts. Only on what I call a mixture integral. And what I mean by a mixture integral are integrals that are, and they're products, usually products, but they have two different types of functions. For example, if you think of some of the ones you've done in class and in here, x is an algebra thing to me. And if it's multiplied by e to the x, that's what I mean by a mixture integral. You have two different types of functions, or maybe you have an x and an ln of x, right? Two different types of functions, or an x and a sine x. These are all what I would call mixture integrals. And let me throw one more in there just so, how about, what's another one I could do? X times, let's say I had cosine of x squared. Okay. All of these are mixture integrals. And with the exception of this one, if you think about it, this would be a u substitution. Because if you let u equal x squared, du is going to be 2x, which is close to what we have here. I'm just going to make it really obvious, okay? If I let u equal x squared and that was a 2x dx, this is just going to turn into cosine of u, and the 2x and the dx become your du. And that together becomes your du. So my point of this is this. If you have a mixture integral with two different types of functions, what you should first consider is regular old u sub, because that worked on this one, right? This was a mixture problem. That was u sub. But if you try u sub on any of these, you're going to run into a dead end. It's not going to work. So if you get a mixture integral, first try u sub. If u sub doesn't work, it most likely is integration by parts, okay? And we're going to do some more examples of integration by parts. But here's my other purpose for that. This, to me, while it's a product, these are all products too, this is not a mixture integral. This is all algebra terms. And if it's all algebra terms, what I want you to, don't even think integration by parts, okay? I'm going to put no, okay? And here's why. What is true is you can take a product, you probably could use integration by parts on this with some, let u be one part, dv be the other part. But if it's all algebra terms, I claim there's usually a better way than using integration by parts. So I like to just reserve integration by parts when it's a mixture integral after I've tried u sub. So if integration by parts is not an option, and we know we have a product here, what we're going to have to do, and we can't distribute anything, we are going to have to do a u substitution. So what would I let u equal? Well, things in parentheses are usually good choices. And this 2 plus x is being really in parentheses raised to the 1/2. So I'm going to let u equal 2 plus x. And then we know du dx, but we always just multiply the dx over to the other side. The derivative of 2 plus x is just 1, huh? Because that would go away, and this is just 1. So it's just 1 times dx, or just dx. So let's rewrite this integral, because we did one like this before, but I wanted to do another one to show you. This x squared so far is unaccounted for. But right now, 2 plus x is what I'm calling u. So that is now u to the 1/2. And this dx is just a straight up match for du. I could just trade that in for a du. And so after I do my u sub, notice I still have a leftover x. So if you weren't here, I don't remember when I did that, sometime last week. If you have leftover x's, it's sometimes still okay, as long as I can write this in terms of x. So who knows, what could I replace this x with? What would x equal? Type it in the chat. Like if I wanted to get this in terms of u, what does x equal? It's going to be something squared, right? Okay. Leftover x. And if you have leftovers, I know you haven't seen a whole lot of these, but that's why I wanted to make sure I do one. I haven't seen a whole lot in class, I should say. You can always go back to here, because if u equals 2 plus x, what does x equal then? X would equal, okay, now I'm seeing it in the chat. X would equal u minus 2. And so if I have leftover x's after I've done u substitution, that's an option, is go back here, solve for x in terms of u, and now you've got something to replace them. So this is now u minus 2 squared times u to the 1/2 du. Oh, somebody came in and then left. Wait. Did I miss them? I missed them. Okay. Now from here, this is all just doing some algebra and simplifying this. I'm going to have to square this out. I still have a product, right? I still have a product, but what's better here is if I FOIL this out, I could then distribute the 1/2. So most of you can FOIL that out in your head, right? U minus 2 times u minus 2 is u squared. You're going to end up with a minus 2u and a minus 2u, so that's minus 4u. And then you're going to end up with negative 2 times negative 2, which is plus 4. And then we would distribute this, so we can just get powers. And remember, you're going to have to add the exponents. So I like to work in fractions. I know 2 plus 1/2 is 2.5, but you could, in fractions, that's 4/2 plus 1/2. So I'd like to think of this as u to the 5/2. This is u to the first times u to the 1/2. So that, think of that as 2/2. 2/2 plus 1/2 is 3/2. And then once you get them all written like this, you're just using your old power rule where you add 1. So this would be u to the 7/2. If you catch yourself, right, you could either divide it by 7/2 or times 2/7, right? So you don't have to rewrite. I'm running out of room here. So minus 4 u to the 5/2 if I add 1, divided by 5/2 or times 2/5. And then another 4 u, add 1 to 1/2 gives me 3/2, divided by 3/2 or times 2/3, plus a constant. And then your last bit would be substituting back in what your original choice for u was, which was the 2 plus x. So I'm going to have 2/7, 2 plus x to the 7/2. And we'll simplify along the way. 4 times 2/5 is 8/5. That'll be to the 5/2. And then this is 8/3. Plus a constant. How's that? All right, so then let's try this next one. See, now immediately my radar is going here because I see ln and I see an x squared. So this is a mixture integral to me, right? This is a mixture. But remember, you don't necessarily go straight to integration by parts. It's worth considering a u sub. And maybe what I'll do here, since usually when you have integration by parts, we have it's a multiplication problem, and this really is, but I'm going to emphasize that by writing it as a multiplication problem, ln of x times 1 over x squared dx. If I tried a regular u sub, I would let u equal ln of x. And the trouble is my du is 1 over x dx. 1 over x dx. But what do I have left over is 1 over x squared. Okay, I could borrow an x here, right? I could think of this as 1 over x times 1 over x and have a leftover x. And we just saw that it's sometimes okay to have a leftover x. But almost always, if it's a mixture problem and u sub doesn't seem to work out, it's probably going to be integration by parts. So I'm going to put doesn't appear to work. There we go. So therefore, I'm now switching over to integration by parts. So that's one frustrating thing. I mean, we've talked about this about integrals is there's no definitive, I can't tell you if you're searching for rules like you're going to always do u sub if it's this or always integration by parts. They're not as clear cut with antiderivatives. All right, so assuming now we're going to do integration by parts, maybe I'll switch colors to, we need a u and we need a dv. And remember, your criteria for choosing u is which of these is going to become simpler when you take the derivative of it. And if it's got an ln in there, that's always going to be your u, because the derivative of ln is, we saw, is 1 over x. And what's nice about that is there's no more ln's, right? So in my book, that's way simpler to deal with after I take the derivative. And if you tried this, that would actually get worse if you took the derivative of that. So we're going to let u equal ln of x. Du is 1 over x dx. That leaves dv to be this part, but I'm going to have to integrate it. So knowing that I'm going to have to integrate 1 over x squared, I'm going to write that as x to the negative 2 dx. Because my antiderivative says I got to add 1 and divide by that. And if I rewrote that, that's the same as negative 1 over x. And so that doesn't look like a negative 1. There we go. Still doesn't, but that's okay. And so remember, my formula is, my answer is uv minus the integral of v times du. So then it's u times v, so ln of x times negative 1 over x. Minus the integral of negative 1 over x is v times du, which is 1 over x. Now, don't make this mistake, because I guarantee there's going to be a few people do this, because I see it all the time. It's very common, is to say, oh, I know the antiderivative of that is ln, and that's ln, so it's ln of x times ln of x. Remember that when you have a product, you can't just integrate one and integrate the other one. You can't do that, right? So instead, what you want to do is simplify this. I'm going to pull out this negative, so this negative is going to come out and make this positive. And what does that leave me with? That leaves me with 1 over x squared, which we integrated that earlier, right? If I just think of that as x to the negative 2. Then that's just going to integrate to this, because we did it right here. So we're going to have ln of x. And then this integrates to minus 1 over x. After you simplify it, I'm just going to point you up to here. Plus c. Done. So that leads me to, what I try to do is think like a professor, think like a teacher, right? If you've got 24 minutes on a quiz or a short test, are the quizzes the same length? Or no, those you do on your own. How long are the quizzes? Are they timed? I should know that. 20 minutes. Okay, so they're short. They're less. Okay. Yeah, I mean, so some questions can get really, really long that you do on homework. So I try to think of ones, what are ways professors can assess you that you understand something without making it super, super long. And this problem caught my eye in 5.5. It wasn't one of the problems that was suggested, but it still struck me as one that could be a type of thing where it really shouldn't take that long. And it's assessing the same skill, but just in a different way. This is number 37 in 5.5. So suppose you had all of this information and you were asked to find the integral from 1 to 4 of x times f double prime of f of x. And I guess the thing to think about here is, how are we going to evaluate this integral if we don't even know what this function is? We just know the second derivative. The thing to notice here, I think, is that this right here, this is what I would say, is a product. And we've seen products can be really handy when you're using integration by parts, right? A lot of times when we're doing that, that's what we're doing. Not all the time though, right? I should just to point out, right? This was a product too, wasn't it? That's a product too, but that means we didn't use integration by parts on that one, huh? The second one we did, we can think of as a product, and integration by parts worked. But let's approach it as integration by parts, which means to do this integral, we're going to have to choose a u and we're going to have to choose a dv. And the usual criteria is which one's going to become simpler when you take the derivative. Well, we might have to throw that out the window. How about this? If I let, kind of like trial and error here, if I let u be f double prime of x, wouldn't du be the third derivative of that, right? But we know nothing about the third derivative. We know something about the first derivative, which I could get by taking the antiderivative of that. So it's kind of then implied here that I should let dv be f double prime of x, so that when I integrate it, I get just f prime of x, which means my u is going to have to just be x. And du would be dx. Does that make sense of how you would think about that? Just look at your given information, right, and see what would be useful. So then we're going to have, I'll write it again, the format again, uv minus the integral of v du gives us x times f prime of x minus the integral of f prime of x times du, which is dx. And we never did any on Friday when we talked about integration by parts, about like how do you handle a definite integral? The way it works is, when you do this integral, which is part of the formula, it's still going to have the same bound. So that's going to go from 1 to 4. And this part right here will be evaluated also. We don't need that's already, it's not in an integral, but that will be evaluated from the same limits from 1 to 4. So let's just bring this down. This will be x times f prime of x evaluated from 1 to 4 minus, but what's this equal to? And, earlier in the quarter, we were talking about the integral, meaning like the limiting Riemann sum. But pretty much from now on, associate that with antiderivative, right? That's what we're using. So what is this saying? What is the antiderivative of the derivative of f of x? If you think of it that way, the antiderivative of the derivative, those guys are just going to cancel each other out. That's just going to give me f of x evaluated from 4 to 1. Same limits. Does that make sense? And then I could just plug in. So this would be 4 times f prime of 4 minus, so let's just do this separately, minus, I have two minuses now, minus 1 times f of 1. I don't know why I did that. There we go. And then this is going to be f of 4, right? You plug in the top limit minus what you get for the bottom limit. And all this stuff was given up top. You probably have, I have to zoom this out to see it. All this stuff was given up top. So you have 4 times f prime of 4 was given to be 3 minus 1 f prime of 1 is 5. And then minus, let's just keep this, f of 4 was 7, f of 1 was 2. 12 minus 5 minus another 5. I think the final answer should be 2. Is that better? No? Uh-oh. Is my video going out? I was having problems last week. You can see my, okay. Uh-oh. Maybe yours is, Arjun. Okay. Well, it'll be any part that's fuzzy, it'll be on the recording too, so you can check that out. Okay. This goes under the category of just covering all of our bases. One of the examples in integration by parts, I think it was example 4. I know how class works is I think she's looking at what questions you have, you know, from the surveys and stuff and focusing on those. So maybe it's because nobody asked a question on it. But this type of an integration by parts integral is a little bit tricky and a little bit different. I'll put similar to example, I think it's 4. Yeah. Example 4, page, this is in your book, this is page 364. Okay. It's definitely a mixture problem, right? It's definitely a mixture. And I don't see a way a u sub's going to help us out of this mess, because if I let u equal this, this is no way that's going to be du. And if I let u equal this, there's no way that's going to be du. So it's going to have to be integration by parts. So what will our, let's do it right here. We need a u and we need a dv. And even here, my criteria for u is which one's going to become simpler when you take the derivative. Well, the derivative of e to the 2x is 2e to the 2x. That's not really any simpler. And the derivative of sine of x is cosine of x. That's not all that simple, right? That's not much simpler either. And so the truth is when you have an exponential function and a trig function, I know some of you are, I heard it mentioned in class, that Liate thing. Some of you may know that as like kind of a guide to who should be your u when you take u substitution. When you're doing integration by parts. The truth is the t and the e could interchange. You could have, if you have one with a trig and an exponential, you could let u equal either one. We just usually put the t first because it looks like it spells a word. So I don't know, the way I see it, well, I guess the derivative of sine is cosine. That's better than 2e to the sine x because you have an extra constant. So maybe I'll just default to Liate and let u equal sine of x. That means dv is going to be e to the 2x dx. This is cosine x dx. Okay, and this one big thing we spent time on Friday was talking about your mini u substitutions and being able to do those in your head. One way to explain the antiderivative of e to the 2x dx is to do a u substitution, but that takes a lot of time and we're already got a lot to do on here. So if it's just a constant times x, it's going to be 1/2 e to the 2x. That's one of the things we spent time on Friday. And you should be able to figure those out without writing them out if you want to save some time. Okay, so then we have uv minus the integral of v du, uv minus the integral of v du which is, okay, now I could leave this, I could factor this constant out if I want to. I think I might just leave it there just to make less work later on. But notice in this integral that I still have to do here, I have e to the 2x, but this time it's times cosine of x. And so it's another integration by parts. I don't know. Do you want me to pull out the 1/2? Oh, why? How? Well, here's the easiest way to explain. Just do it backwards. What is the derivative of 1/2 e to the 2x? If I took the derivative of that v prime, it would be 1/2 e to the 2x times 2. So the 2 and the 1/2 would cancel, and I get right back to there. So when you take the derivative, if it's just a constant times x, it's just going to be 1 over that constant. That's something to practice. All right. So we're going to need another integration by parts here. And you might be getting a little worried now because you're probably noticing when we did integration by parts here, all that happened was this changed to a cosine. This didn't go away, right? I have a 1/2 now, and so if I do it again, you're probably getting a little bit worried. And that should be concerning, but there is a way out of this. So let's let u equal the trig function again. U equals cosine of x. That means we're going to let dv, again, you can factor that out if you want to, but then you're going to have to keep track of that 1/2 in front. My inclination is to just leave it there because the antiderivative of 1/2 e to the 2x, we know the antiderivative of e to the 2x itself is 1/2 e to the 2x. And so if there's another 1/2 there, it's going to be 1/4 e to the 2x. Right? Because without that 1/2, it's 1/2. And then there was a 1/2 already sitting there. So just multiply those 1/2s together. The derivative of cosine is negative sine of x. And so now we're going to have, this is still going to stay here, right? That's coming down. Minus, and here we got to account for this because we're about to do a whole nother uv minus the integral of v du. So that minus sign is going to apply to everything right here, everything we write here, which is uv cosine x times 1/4 e to the 2x minus the integral of 1/4 e to the 2x times negative sine x. Let's clean this up before we get a little too worried here, right? Because you're probably seeing this is going to go on forever because you still end up with an e and a sine. But let's clean this up. So maybe I'll bring this down now. So I have sine x 1/2 e to the 2x. Let's distribute this minus. So this will be minus cosine x 1/4 e to the 2x. Okay, ready? I'm going to do a bunch of things here. So I want, because it's going to take too long. If everybody watching here, this negative and the 1/4 can come out. And if the negative and the 1/4 comes out and there's already a negative there, that's going to be positive 1/4, right? But then I'm about to distribute this other negative. Does everybody see that this is going to be right back to negative 1/4? Right, negative is positive, but then I bring that negative in, it's back to negative, and the 1/4 comes out. Okay, So now here's the kind of we're almost done, believe it or not. And that seems weird because we ended up with the same integral we started with, and it just seems like this infinite cycle that's going to keep, if we keep doing integration by parts, it's never going to end. But it actually means we're almost done, which is weird. So here's the solution to this type of integration by parts integral. All of this was an attempt to answer what integral? Let's rewrite the integral we were trying to do. The integral we were trying to do was e to the 2x times sine of x dx. And here's the way we can think of this. If this integral had limits on it, if I had limits on it, I don't here just because it would have gotten too long. What is your final answer always to a definite integral? What is your final answer always to a definite integral? How many people agree the final answer is just a number, right? Anytime you evaluate a definite integral, the final thing is just a number, or maybe the sum of some numbers, but it's just a number. So let me try this and see if this works. I don't have to explain it this way, but pretend that this is just a number. And why don't we call this I for integral? This just means I, that's the value of that integral. Here's what I see. This says I equals some stuff minus some stuff minus 1/4. What is that? Isn't that just I again? If my goal is to solve for I, right, I'm supposed to evaluate this integral, how would you do this algebraically? What would you do with this I right here? Think of algebraically. What would you do? How many people agree you would get the i's on the same side, right? Like if that was x you were solving for, you would combine. So you would add 1/4 I to both sides. Now, I'm trying to get, I know that's going to be there, that's going to be there, right? That's this. But when I move this over, it cancels. What is 1i plus 1/4 I? Do a common denominator. How many fourths is 1i? That's 4/4, right? 4/4 plus 1/4. This is going to give me 5/4 I equals, I'll keep the color coding here, this minus this. And again, what's in this blank is up here. That's this and this. So what is I by itself? What would I do to get I by itself? I would either divide by 5/4, which is the same as multiplying by 4/5. And that is the answer. And we just stick a plus C on the very end. So let me, again, by I mean the integral of e to the 2x times sine x dx is just going to equal 4/5 times sine x 1/2 e to the 2x minus cosine x 1/4 e to the 2x plus some constant. It's a very unusual type of integration by parts, right? That's not like how the other ones go. The good news is, for one, I would say it's pretty low on the scale of showing up on a 20-minute quiz or a 24-minute short test. However, what made this one a little bit longer was me putting the 2x there, which made these antiderivatives a little bit weird. You had to get the 1/2 and the 1/4. If it was just e to the x times sine of x, which I think is what example 4 literally is. Let me check, yeah. This is the book here. Example 4 is just e to the x times sine of x. That one plays out pretty quickly. And I could totally see that being a quiz or a test question. So this technique, technique where you get the same thing, right? Kind of review what we did. You did integration by parts twice. You ended up with the same integral that you were solving for. And so then you just added it over to the other side. That's always going to happen. For integrals if you have an integral like an e to some x times a sine x, or e to an x times a cosine x, something like that, you're going to want to, that's the technique you're going to use. And I would practice some. There's some in you can spot them in the book if you can pick. Well, let me see if I can see one for you. Recommend one for you to do. I would do of course they don't have them right there. It would be, well, the one that shows up on the one that she recommended, number 35 in 5.6. That was one of her recommended problems, so I would definitely try that one and make sure you can do that. In the 10 minutes or so we have left, I'd like to give you a little insight into partial fractions, because I think I have some tips that might make this go a little smoother. So yes, stew on this a little bit, go back and look at it and make sure you understand it. I know that's not the easiest one, but we're just trying to cover all of our bases here. Okay. By the next short test, you will have U sub to think about, integration by parts to think about, partial fractions to think about. You're going to have 3 big techniques. So, but remember what I said, only consider integration by parts if you have a mixture, 2 different types of functions. Here, we're back to just all algebra, right? That's all x's. So don't even consider integration by parts. The first thing you should consider is U sub. And if I were to try a U sub, the only logical thing I think I would choose for U is the denominator. And the trouble is my derivative is 2x plus 6, which even if I factor out a 2, that leaves me with 2 times x plus 3. And there's nothing I could do to an x plus 1 and make it look like 2 times x plus 3. So remember, you're only allowed to, if you've been coming, the way I teach it is wish. You're only allowed to wish for a constant in front here, the multiply. There's nothing that would turn it into this. So U sub is not going to work, but it's definitely worth giving it a quick look before you jump in, because as you saw, partial fractions is a little bit longer. The next thing to notice is, does the bottom factor? Which it does. So if the bottom factors and U sub doesn't work, I'll put yes, then it's going to be partial fractions. And so what we typically do, you saw that in class, is let's just take a break from the integral for a second, take a break, and we're just going to work with this one fraction. And here's kind of the idea of partial fractions. I've just got a piece of scratch paper here. I'm just going to scribble some stuff out here so you don't, it's nothing more than this. You've been adding fractions your whole life. You know that when you add 1/2 plus 1/3, you at least know the denominator is going to be 6, right? And after you find your common denominator and do this stuff, you can figure out what the numerator is going to be. It's going to be 5, 6, okay? But the idea of partial fractions is going the other way. So let's say I had 10 over 21, and I wanted to think of this as the sum of 2 smaller fractions. It's actually kind of a good, I'm surprised. I mean, I don't remember doing that when I was in grade school. I wish the teacher would have had me do that, kind of go the other way. Could you at least tell me what your denominators are? What would your denominators have to be? if you went the other way? How many people agree 7 and 3? And how do you know that is the factors of 21 are 3 and 7, huh? So 1 would be 3, 1 would be 7. And what she was doing, and what this, not just her, that's how we do it. We temporarily call this numerator A, this one B, until we figure out what A and B are, right? Now go find A and B, and then you can figure it out, right? That's exactly what we're doing here. Because x plus 1 over, I wish I would have factored that. That's really, what does that factor into? X plus 2 times x plus 4. We're going to split this up into two smaller fractions. One of them is going to have a denominator of x plus 2. We know that's how the way you add fractions. And the other one's x plus 4. Right? Because if we combine those, that would give us this denominator. And we'll temporarily call the numerator this one A and this one B. It doesn't matter if you put A over x plus 4 and B over, if you switch, it doesn't really matter. Now, here's where I would probably change. Different math people, there's nothing wrong. We just see it differently, okay? I like to think of a faster way to solve for A and B than what you solved, the technique you did in class. And Dr. Burke doesn't care. As long as you can do this problem, if you've got a slightly more efficient way than what she taught, that's fine. And in fact, given the nature of the short quizzes and tests, it's really in your best interest to find a more efficient technique, right? So here's what I would do instead. And I'm going to rewrite this even just because this is in the way. Okay, what she did in class, what you did was you combined this to a single fraction using your common denominator skills. That's one technique. But here's what I would do instead. How many people do not like fractions? They're not your favorite thing. And if you could see my camera, my arm is up. I'm a math teacher. I'm supposed to like fractions, but I don't really care for them. So any chance I get to get rid of my fractions, I'm going to take. Because this is an equation, if I multiply both sides by the lowest common denominator of the whole entire problem, which is just x plus 2 times x plus 4. How did that change to a 3? I have no idea. Which is x plus 2 times x plus 4, I'm going to get rid of all my denominators. Because on the left side, they just cancel out, leaving me with x plus 1. On the right side, when you distribute this into the first fraction, do you see that the x plus 2s are going to cancel? Because there's 1 down here, there's 1 here. So that's just going to leave me with a times x plus 4. And when I distribute it into the second one, the x plus 4s are going to cancel. So it'll be b times x plus 2. The next thing I'm going to do differently, the way she explained to solve for A and B is a technique that the book uses, which I find a little more tedious than it needs to be. So here's another technique, which is a valid technique. Other calc books use this technique, is to do this. This is an equation, which means the left side and the right side have to equal each other for any value of x, right? If it's an equation. So what I'm going to do is I'm going to substitute in. I'm going to pick a nice x value. I'm going to let x be -4. If x is -4 on the left side, I get -4 plus 1 is -3. I get a times 0, right? That's why I chose -4, because it's going to wipe out that term. And then -4 plus 2 is -2b, right? -4 plus 2. And right away, I see that -3 equals -2b. So what would b have to equal? If I just divide by -2, b is equal to 3/2. So I've got b. Now I want to solve for a, so I'm going to do the same thing over again, but this time, guess what I'm going to pick? On this one, I picked -4 because it made this term 0. So now what I'm going to do is pick -2. Yeah. -2 plus 1 is -1. -2 plus 4 is 2a. And then this term is going to be 0. So now I've got a is equal to -1/2. And this was my goal. I wanted to solve for a and b so that I could put them back in here. And the whole idea of this is we're just rewriting. This is something we couldn't integrate, but if this equals the sum of these two fractions, we're now going to be integrating a, which was -1/2 over x plus 2, plus b, which is 3/2 over x plus 4. Oh, let me slide that up. And after you get good at these, I know it's hard because things are going really fast. You'll see you don't really have to rewrite it, but if it helps to see this, by all means do it. You could bring out the 1/2, separate this into two separate integrals. But what are each one of these? What type of integrals? If you do a little mini u sub in your head, in other words, if you let u equal x plus 2, du is going to be dx. This is just 1 over u du. What does that integrate to? Or I guess you could say, think the other way. What function would have had a derivative of 1 over x plus 2? That's an ln. Exactly, that's an ln of the absolute value of x plus 2. Plus 3/2. This is another ln. You get a lot of ln integrals when you do partial fractions. What she showed you on one of them is, she talked about the log rules. Most of the time, this is fine. There's no reason to do any more work on this one. It's done. What I think she was trying to say is that if you, like every good student, if you're going to look in the back of the book on if it's an odd number problem, they may rewrite this with the log rules, and it might look a little bit different than this. But this is totally fine. You've got your antiderivative, so you don't have to do that, I guess, is what I'm saying. For sure, yeah. So we definitely got to do more practice with integration with partial fractions, but we can do more on Wednesday. And I suppose also, what was it? The table of integrals was the other thing that was the topic for today. We can do 1 or 2 examples there. But hopefully this will help. And I'll go ahead and stop here. Any questions on anything? First steps are just to rewrite it and then yeah, that's what I do. Yeah, I just, the minute I recognize it's partial fractions, I just ditch the integral and just work with this and break it down. And once I figure out what a and b are, then I bring the integral back. Sure thing, yep. I've got office hours from 2 to 3 as well, so if anybody wants to check that out. And tomorrow morning.